Chapter 18, Ethers and Epoxides, Thiols and Sulfides. An ether has two organic groups bonded to the same oxygen atom. Some ethers have been used as solvents. Here show some examples of ethers. Diethyl ether, methyl phenyl ether or anisole, tetrahydrofuran or THF. Simple ethers are named by identifying the two organic substituents and adding the word ether. For example, the first one has a isopropyl methyl. The name is isopropyl methyl ether. The second one has an ethyl, has a phenyl, and so it's called ethyl phenyl ether. Okay? If the molecule has a complex functional groups, then the ether part is considered as epoxide substituents. For example, the first one you have two ether part with a benzene. In this case, it's called diperyl dimethoxy. So the ether part now becomes substituents called methoxy, dimethoxy benzene. Okay, second one has a cyclohexene, and this ether part here is tertiary butyl. So it's called number 4 carbon has a tertiary butoxy. So butoxy number 1 cyclohexene. In ether molecules, the oxygen atom is sp3 hybridized. The ideal angle in sp3 hybridized molecules is 109 degrees. In dimethyl ether, the angle is 112. Although the carbon-oxygen bond is polar, but these two bonds are symmetric, so they cancel most of the polarity, and the whole molecule only have a slight polarity, so very small dipole moment, and the consequence is that the ether molecules has low boiling point compared to the alcohols with the same number of carbons. In this section, we study 3 methods to synthesize ethers. The first method is acid-catalyzed dehydration of alcohols. 2 alcohols lose a water molecule, forms an ether. In the second method, called Williamson ether synthesis, an alkoxide react with alkyl halide. Leaving group leave give you an ether. In the third method, called alkoxymercuration of alkene, a double bond react with mercury acetate with an alcohol, okay, followed by sodium boron hydride in base, give you a ether. Here shows an example of using the first method to make ethers. When ethanol is treated with sulfuric acid, 2 alcohol lose 1 water molecule. A diethyl ether is synthesized. Here shows the mechanism. First, 1 alcohol oxygen is protonated by the acid. Okay, so in this case, acid serves as a catalyst. It protonates the oxygen, forms a good leaving group, and then the second alcohol attack the positive charged carbon, and the leaving group leave. So this is a SN2 mechanism, all right, and then followed by deprotonation of this hydrogen by a water molecule, and that gives you diethyl ether. Now this method is simple, however, it is limited to use with primary alcohols because it involves a SN2 reaction. It attack on the carbon, and the second, if the alcohols are secondary and tertiary, then E1 dehydration will take over the reactions, give you alkenes. The most generally used method of preparing ether is the Williamson ether synthesis. In this method, first an alcohol is treated with sodium hydride. As you know, sodium hydride has a hydride that is a strong base, which can deprotonate the hydrogen from the alcohol, forms an alkoxide. And alkoxide, just like hydroxide, which is strong base, which is also a strong nucleophile. And this nucleophile attack alkyl halide, undergo SN2 mechanism, leaving group leave, forms an ether. Now you may remember in the last chapter, we can protect alcohol by forming trimethylsilyl ether, and the reaction is also SN2. So a tertiary amine deprotonate the hydrogen, and oxygen attack silicon, chlorine leave, and give you OTMS. Alternatively, ether can be synthesized using silver oxide instead of sodium hydride. And in this case, the reaction can finish in one step instead of two steps. An example is alpha-D-glucose, which is alcohol, react with methyl iodide and silver oxide. The hydrogen bonded to oxygen is replaced by this methyl group, forms the methyl ether. Since the Williamson ether synthesis is SN2 reaction, the alkyl halide can't be crowded, sterically hindered alkyl halide. Suppose we want to make T-butyl methyl ether. Then the smaller side, the alkyl methyl group, must come from alkyl halide. And the larger side can be butoxide. Only in this way, SN2 reaction can take place. If you choose the opposite, the alkyl halide, the larger side comes alkyl halide, which is tertiary, then the reaction, instead of SN2 reaction, it goes to E2 elimination, and a double bond is formed instead of an ether. The third way to synthesize ethers is similar to oxymercuration-demercuration method we learned in Organic 1. In oxymercuration-demercuration method, a water molecule is added to a double bond. Hydrogen adds to one carbon, hydroxy adds to another carbon. This reaction obeys Markov-Nikov rule, and the reagents includes a mercury acetate with water. Now, organic solvent sometimes also added. And second step use sodium boron hydride. So in the mechanism, the first step is mercury acetate adds to this double bond, forms mercurian ion. And in the second step, water serves as a nucleophile, which attack one of these carbon, bond between carbon-mercurian break, forms organomercurian compound. And then next step is a hydride from sodium boron hydride, attack carbon, and the carbon-mercury bond break, so the mercury is replaced by hydrogen and an alcohol is produced. Note that this hydroxy group comes from water attack. Okay, so what if in the solution, instead of water, we add alcohol, for example, CH3OH? What will happen? If water is replaced by an alcohol, in this case methanol, then the product is an ether. So in the mechanism, the first step is the same. Mercurian ion is formed, but the difference is the second step. instead of water, now it's a alcohol, methanol. Oxygen serves as a nucleophile, attack this carbon, bond break, give you organomercury compound, and in this compound, methoxy is added to the molecule. And the next step, sodium boron hydride provide hydride which attack this carbon, replace the mercury, so the final product is an ether. And this method is called oxymercuration of alkene. Here shows an example of epoxymercuration of alkene. This reaction requires two steps. The first step, mercury acetate, and an alcohol, in this case is methanol, followed by second step, sodium boron hydride. So as we saw in the last slide, it first forms organomercury compound, and then mercury is replaced by hydride from sodium boron hydride that give you the ether. And note that when we use methanol as the alcohol, the product is a methyl ether. Suppose we want to make ethyl ether, C2H5. Then the alcohol should change to ethyl alcohol. Okay. Also note that in the first step, we use acetate, so mercury acetate. The acetate has this structure. Okay, so this is called acetate. All right, so this combined with mercury, that's mercury acetate. Now, you may also see sometimes all the hydrogen is replaced by fluorine, so CF3, and that would call the trifluoroacetate, and that also commonly used for the first step. Okay, and the reaction obeys Markov-Nikov addition rule, just like adding water hydration. Here, hydrogen adds to the carbon that has most hydrogen, and then methoxy, in this case is methoxy, goes to the carbon has fewer hydrogen. Practice. How would you prepare ethyl phenol ether? Use whichever method you think is more appropriate. We have learned three methods to make ethers. The first method, we combine two alcohol, lose a water under acidic condition. But that method apply only for simple alcohols. Okay, so the ether made is a symmetric ether. But in this case, the ether is not symmetric, and so this is not appropriate method. Now, second method is Williamson ether synthesis. In Williamson ether synthesis, it's the epoxide attack a alkyl halides. So the reaction is SN2 reaction. Alkyl halides must be primary, less hindered. In this case, the ether part, okay, that may come from the alkyl halides. So this may be CH3, CH2 bromide, okay, and the other side, epoxide. So that will epoxide attack this carbon, leaving group, leave, and that will give you the product. But first, we need to deprotonate this hydrogen. So we start with phenol, okay? We deprotonate this one. Now remember, for alcohols, we use sodium hydride, strong base, to deprotonate the hydrogen. But the phenol is much stronger acid than usual alcohols. And in this case, we can simply use sodium hydroxide. That is good enough to deproton this one, forms epoxide, and then attack second step, add alkyl halides, and that will give you the desired ether. Okay, so second method works. Let's think about the third method, epoxymercuration, demercuration. For that step, you need a double bond. You also need a alcohol. So left side is a benzene ring. Benzene ring cannot have a simple double bond, and therefore the right side can be CH2, CH2. You have a alkene, and then the alcohol must be the phenol. Okay, so hydrogen adds to one side, alkoxide adds to another, and that give you the product. All right, so the reagent is you add a phenol, you follow two steps. The first step is mercury acetate and ethylene. Now in this case we use trifluoroacetate as we shown in the last slide. Okay, so that's the first step, followed by second step, sodium boron hydride, and that will also give you the final product, ether. In summary, we have studied 3 ways to synthesize ethers. The first method is acid-catalyzed dehydration of alcohols. In this method, 2 alcohols combine, lose a water molecule, forms a symmetric ether. This method is appropriate to primary simple alcohols. In the second method, which is Williamson ether synthesis, an alkoxide react with alkyl halide, undergo SN2 mechanism to form a ether. The product, smaller part, comes from alkyl halide due to the SN2 reaction. Alkyl halide is preferably to be a primary alkyl halide, and the larger part in the ether comes from alkoxide. Alkoxide is synthesized by alcohol using strong base such as sodium hydride. The third method is called oxymercuration of alkene. This method resembles oxymercuration demercuration. In that method, we follow 2 steps. One is mercury acetate with water, followed by sodium boron hydride. The net effect is hydrogen adds to 1 carbon, hydroxy adds to another carbon, forms an alcohol. In oxymercuration of alkene, water is replaced by an alcohol, and the net effect is hydrogen adds to 1 carbon, alkoxide adds to another carbon, and that gives you an ether. This method follows Markov-Nikov rule, and that means hydrogen adds to the carbon has the most hydrogen, but alkoxide adds to the carbon with the least hydrogen. Here are the homework problems.